Alrighty, here we go. Once more unto the breach, dear friends. So this is a Chapter 2 review. It's going to be your final lesson in Chapter 2. It's just kind of, in lieu of a test that you're taking. So, again, kind of the same thing. I'm going to walk you guys through this. Hopefully, you'll have the opportunity to sit there and kind of figure it out for yourself. And then if you guys need help, here's the video. If you guys don't need help, then you're good to go. So, once you're finished with this, next week we're going to start on Chapter 3, and that is parallel, perpendicular lines, stuff like that. Still proofs involved, unfortunately, but not as many as Chapter 2. So, let's get going here. So what I'd like you to do is try and figure out let's look at 1 through 4 first. And so take a couple minutes, try and get through those, and then we can check your answers. So now hopefully we're back. A little bit of time has passed in your land. It's been about 3 seconds here. So, when we're looking at this, what we want to do is try and figure out the pattern. So when I look at this, I see that they're basically on both of these. Well, let's start with number 1. They're basically 2 patterns here. You have the pattern of 5 to 7, 7 to 9, 9 to 11. Then you have the pattern of 1 to 0, 0 to negative 1. And what that pattern is when we do that, we're adding 2 each time. 5 plus 2 is 7. 7 plus 2 is 9. Plus 2 is 11. And so the next one in that group is going to be 13. Now on the other side, we are subtracting 1 each time. 1 minus 1 is 0. 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2. So here are going to be your answers. Negative 2, 13. Those are going to be the next 2 terms. Moving on to number 2. Again, what we have here is we're going to add 4.5 plus 0.5, and we get 5. Then we go up from 0.5 to 0.6. Add those 2 together, we get 5.6. Up from 0.6 to 0.7, add those 2 together, and we get 6.3. So then we're going to go up from 0.7 to, that's right, 0.8. Add those 2 together, 6.3 plus 0.8 gives us 7.1. And that's that. So now let's look at number 3. Number 3 is asking us to find what's called a counterexample for each statement. Don't know what you guys went over regarding counterexamples, but a counterexample is just an example that makes the statement not true. In mathematics, we worry a lot about precision. We try and be very precise with our language. So everyone knows what we're talking about when we're talking about it. And so something is either 100% true or it's false. So if we look there and say that an apple is a red fruit. Now, I'm going to be honest, most apples are red or reddish. But not all apples are reddish. So a counter example to this. So we're not saying that all red fruits are apples. So, we don't want to be saying like strawberries or cherries or something like that. We're saying that all apples are red fruit. So we're looking for an example of an apple that is not a red fruit. And I'm going to say Granny Smith. Because a Granny Smith is definitely an apple. It's just not a red fruit. It's a green fruit. Now, moving on. A parallelogram has 4 congruent sides. Then it is a square. Now, a square is a parallelogram, and it has 4 congruent sides. But that's not all a square is. A square also has 4 right angles. So what we need to do here is we need to keep those 4 congruent sides, and again, congruent means they're the same length. And we're going to take that top and we're going to slide it. So we're going to end up with a parallelogram looking like this. Now here's the thing, all those sides are still going to be equal because we just slid it over a little bit, but we no longer have the 4 right angles which make it a square. Excuse me. This is called then a rhombus. Okay, so again, if any of that didn't make sense to you, if you need that gone through again, raise your hand and whoever the sub is will just rewind it, play it again for you to your heart's content. Also, if you are ever super bored or working on homework or anything, this is online. Stephen Renard, StephenRenard. That's the YouTube channel, and you can just go there and watch these as much as you like. Hey, they're even, and I'm not even joking, I tell kids this all the time, if you're ever having trouble sleeping, put one of these on, it'll knock you out in a heartbeat. Okay, moving forward. And just so you know, people have actually done that. So, next we're looking at writing the converse, inverse, contrapositive for each true statement. Now, I'm going to be honest, some of this stuff I'm probably going to over-explain for you. I wasn't there in your classroom. I don't know how Mr. Bosos taught you. I don't know what you guys are familiar with. So some of this stuff I might be going back too far. If you guys all know converse, inverse, contrapositive really well, then you can just fast forward it, check your answers. What I would like you guys to do now is try 5 and 6 by yourself. Again, 5-10 minutes. Check 5 and 6. Then you can go back, check your answers, or just move on to 7 and 8. Okay, so now that you've tried it by yourself, hopefully, hit pause, try it, come back. So when we're dealing with this, we really have two. So this is a conditional. If a polygon is a triangle, then it has exactly 3 sides. So every conditional has 2 parts. Okay, it has the if part and the then part. The if part is called the hypothesis, and it is treated as a Q, or a P, sorry. And the then part is the conclusion, and it's Q. So I like to color code mine red and blue. So the conditional is if P, then Q, and that's how we say that. We see the P arrow Q, and we read it out loud as if P, then Q. The converse is what we get when we switch around the conditional and the hypothesis. So we're going to go if Q, then P. We then have the inverse. This is what happens when we take the conditional, that's the if P, then Q, the top one, and we negate it. So we say if not P, then not Q. And finally, we have our contrapositive. And there are 2 different ways to look at this. You can either say we're flipping around the inverse, or we are negating the converse. It ends up being the same thing, which is if not Q, then not P. So this is how this would look with this specific conditional. This conditional, if a polygon is a triangle, then it has exactly 3 sides. So for our converse, what we're going to do is we're going to switch those. So instead of saying if it's a triangle, then it has 3 sides, we're going to say if a polygon has exactly 3 sides, then it is a triangle. Okay, so that is the if Q, then P, if blue, then red. So now we're looking at the inverse. The inverse being if not P, then not Q. If not the hypothesis, then not the conclusion. So instead of saying if a polygon is a triangle, then it has exactly 3 sides, we say if a polygon is not a triangle, then it doesn't have exactly 3 sides. Now why the exactly here is important is because a square has 3 sides. A pentagon has 3 sides. They also have 4 sides and a 5th side, but they do have 3 sides. So we want to say, again, we're looking for precision here, so we're going to say it has exactly 3 sides. So finally we have our contrapositive. If not Q, then not P. So instead of saying the converse, which was if a polygon has exactly 3 sides, then it is a triangle, we say if a polygon does not have exactly 3 sides, then it isn't a triangle. Now again, when we look at the truth value here, it's important to remember that something is either 100% true or it's false. So on this one, if a polygon has exactly 3 sides, it is a triangle. Are all polygons with exactly 3 sides a triangle? Sure are. If a polygon isn't a triangle, then it doesn't have exactly 3 sides. Also true. And if a polygon doesn't have exactly 3 sides, then it isn't a triangle. Also true. So all 3 of those are true. Moving on. And again, feel free to pause this if people are having trouble writing it down or getting through it as quickly as I'm talking. Especially because my handwriting is garbage. So if you need to rewind it, I am saying everything out loud as I'm writing it. So if you're having difficulty figuring out what it is that I wrote, just rewind it, listen to me say it as I write it, and that should help you out. So moving on to number 6. So here we have if Jared is in the 11th grade, that is going to be our P, our hypothesis. Then Jared is in high school. That is our conclusion. So I'm not going to go through the whole PQ thing this time. You should have that down if you need to go refer back to number 5. So the converse, we're going to switch the blue and the red. We're going to say if Jared is in high school, then he is in the 11th grade. Okay, now I know some of you guys are already kind of chafing at that. Already sitting there going, that's not true, that's not true. I'm in 10th grade, I'm in 9th grade, I'm in high school. Maybe not that, energetically, because, well, this is a geometry class, but still. So, regardless of whether it's true or not, it's still the converse. The converse is what we get when we switch the conditional's hypothesis and conclusion. Okay, it doesn't have to be true, it doesn't even have to make sense, but we need to know that that's how it's done. We will come back and we'll talk about the truth value later. So the inverse now is what we get when we negate, we say if not P, then not Q. So if Jared isn't in the 11th grade, then he isn't in high school. Finally, the contrapositive, which is if not Q, then not P. So if not blue, then not red. If Jared isn't in high school, then he is not in the 11th grade. So we're going to look at these. The first 2, obviously false. And the last one is true, because to be in the 11th grade, you have to be in high school. Okay? So, let's keep going. So, I'm going to pause a little bit here. I want to explain what a good definition is. And then I want you guys to try out 7, 8, and 9. So a good definition is what you get when you have both a true conditional and a true converse. So what I want you guys to do is I want you to look at 7, 8, and 9, all of them, and kind of view them as an if-then statement. And see if it's true, forward. And then flip it around and see if it's true backwards. Now, if both of those are true, if both the conditional and the converse are true, then it is a good definition. If either one of those is not true, then it is not a good definition. So if that makes sense, the sub can just quick take a poll. I like to do 1 through 5, 5 being I got this, 1 being I have no clue what's going on. If you're seeing mostly 4s and 5s, go ahead and let them try it out by themselves. If you're seeing a lot of 1s, 2s, and 3s, play through the first one for them, and then have them do 8 and 9 by themselves before checking their answers. So number 7, we have a square has exactly 4 right angles. So if we wrote this as a conditional, we'd say if a polygon is a square, then it has exactly 4 right angles. And we look at that, and that's absolutely 100% true. Every single square has exactly 4 right angles. But is that a good definition of a square? Well, let's flip it around and see what happens. We can say if a polygon has 4 right angles, then it is a square. Now, is that always true? And that's really the question we need to ask. Is that always true? And the answer is no. It is not always true, because other shapes can also have 4 right angles, specifically rectangles. So, moving on. Number 8. So we're going to go if 2 angles are supplementary, then their sum is 180 degrees. That is true 100% of the time. So this could be a good definition, so let's check it out the other way. If 2 angles have a sum of 180 degrees, then they're supplementary. Is that true? Well, yeah, that's if 2 angles add up to 180 degrees, that's kind of the definition of supplementary, and that's what makes it a good definition. Because whether it's supplementary angles are angles whose sum is 180, or 2 angles whose sum is 180 are supplementary, it's true both ways. Good definition. Finally, we have horses are animals with 4 legs. So if an animal is a horse, then it has 4 legs. Okay, this is true most of the time. And I know some of you guys are going, well, I know a horse that has 3 legs, and that's fine. Horses can actually absolutely be born or be amputated down to 3 legs. We don't hope for that, but it does happen. But the default here is that horses have 4 legs. So we're going to say that's true. But now we're going to switch around and say if an animal has 4 legs, then it is a horse. And that is absolutely false. Dog, cat, etc., pig, whatever. And that brings us to 14 to 18. Now, yesterday for your bell work, what were you supposed to do? Or not what were you supposed to do? What you were supposed to do is look through the properties of equality and properties of congruence and write them all down in your notes. So those are the properties that we are using here. So why don't you go ahead, pull out your bell work from yesterday, or pull out the notes that you took. I want you to take a couple minutes and try and match these up, 14 through 18. Okay, so now that we're back, let's check to see if you did it right. So with 14, first and foremost, we are dealing with equality here. So that means we can just ignore those pesky properties of congruence, because we have an equal sign, so we're going to be dealing with rules of equality. Now this is if ABC is equal to DEF, then the measure of DEF is equal to the measure of ABC. When all we're doing is flipping things on the different side of the equation, that is called the symmetric property of equality. And again, I'm going to put POE right there. Okay? Next, again, we have an equality here. So when we look at this, what we're seeing is that if we go, so A to B, or AB, the distance from A to B, is equal to the distance from C to D. The distance from C to D is equal to the distance from C to F. Therefore, A to B is equal to E to F. So what we're going to do is we're going to cut out the middleman. And that's going to let us say that AB is equal to EF, And the property that allows us to do that is called the transitive property of equality. Okay. So moving on to 16. So 16, that's where we start. X plus 7 equals 5. And we're going to x plus 7 minus 7 equals 5 minus 7. So we're going to say, hey, listen, what exactly did we change here? And we ended up, what happened is there is now a negative 7 on both sides. So we're subtracting 7 from both sides of the equal sign. The property that allows us to do that is our good friend, the subtraction property of equality. Moving on, if x equals y, okay, so we're starting off with x equals y. And then we're saying if x equals 18, then y equals 18. So, again, we're talking equality here. And this is just straight up substitution. Because what's happening is, so the substitution rule that you should have written down yesterday said that if a equals b, then a can be used or switched out or substituted in for b anywhere it shows up. So here we're saying that x equals y. That means that we can take y and plug it in wherever we find an x. So that means that if x equals 18, we can take out that x, plug in that y, and we get y equals 18. Now finally we have, excuse me, quick yawn. I'm sorry if I made any of you guys yawn. We're going to go, angle A is congruent to angle A. And that is simply called the reflexive property of. Now check it out, because we are dealing with a congruent sign instead of an equal sign, we're going to call it the reflexive property of congruence. So that is 14 through 18. Now 19 and 20, what you're going to do is, I don't know what happened to 21. That's okay. We have 19, 20, and 22. I bet all of you guys are super sad that you're not having to, do more math. Anyway. So, 19 and 20, what we're doing is identifying the angle relationships and then using that to solve for the variable. So again, take a couple minutes, try it by yourself, come back when you're ready. So for 19, what we want to do is we want to identify these as vertical angles. Vertical angles we know are congruent, so we just set it up as 3x minus 63 equals x minus 37. Then all we got to do is solve for x. So we're going to subtract x from both sides. That's going to give us 2x minus 63 equals negative 37. Then I'm going to add 63 to both sides. So we get 2x, 63 minus 37 equals 26. And then we divide by 2, and we get x equals 13. Now again, on some problems you might have to go back and actually find the measure of the angle. If you wanted to check your work, that wouldn't be an issue. So you guys may have realized this already. I just realized my mistake. It is x plus 37. Okay, so when I got x equals 13, I looked back over to the left and went, if I plug that in, I get 13 minus 37, which is going to give me an angle measure of negative 24. Can't have that. What I realized is that in circling x, to show that all we had to do was solve for the variable, I had crossed out part of the plus sign, so I read it as a negative. So, good thing for checking your work. So the process is the same here. We're going to subtract x from both sides, so we get 2x minus 63 equals 37. And then you're going to add 63 to both sides, so we get 2x equals 100. Divide both sides by 2, and we get x equals 50. Now if I were to go back and plug 50 in for both of these, I get 87 down here, and 150 minus 63 up here, which is also 187. So that checks out. So let's move on to number 20. So here, we know that all three of those angles have to add up to 180. We already have 90 degrees of that spoken for, so we know that 5x plus 4x has to equal 90. They are complementary angles. And this is a really easy one. We go 5x plus 4x gives us 9x. We then divide both sides by 9, and we get x equals 10. Okay, and last one, and oh hell, it's a proof. Okay, so it's a pretty easy proof though. We only have 4 things to fill in, and they do most of the work for us. So normally I tell my kids that almost always the first statement in a proof is a given. This is kind of one of those that's not. But we can look, and here we've got the measure of angle ACB plus the measure of angle BCE equals 180. So there's an L in there. I don't really know where the L came from. It's just a formatting thing. When I downloaded it, that's not there. It's just the measure of angle. So the first one is actually going to be that they are a linear pair, and linear pairs are supplementary, and we call that the linear pair postulate. So that's the first one. Got you going. You got 3 more. I really want you to try and do these by yourself. So start off by asking, what changed from the step above? What's different? Why does this have to be true? And then you put that down as your reason, and that's it. So now that you've tried it by yourself, hopefully you got somewhere on it and you're just checking your answers. If not, pay attention. Might learn something, or might not. Anyway, so what we're going to do is we're going to go, what changed from A to B? Okay? What's different there? Well, we replaced our 2 angles with the variable terms from the diagram. And so when we replace things like that, it's just called substitution. Good friend, substitution. Use it all the time. So, now we're going to look down. They do C for us, combining like terms, because what we did is we added 5x and 9x, and we got 14x. So now we're going to go from 14x plus 40 equals 180 to 14x equals 140. Well, what changed there? Well, at first blush, you can see that that 40 disappeared. But you also notice that on the right-hand side, the 180 went down by 40. So what happened was we subtracted 40 from both sides. And the property that allows us to do that is the subtraction property of equality. Not quite staying in the lines, but that's okay. And then we go to G. And so we go, now here, it's a little bit different. So there we have that BCE is equal to 130. And then G says LBC, or the measure of angle BCE. That's not true. It's not the measure. It's just the angle. Angle BCE is congruent to angle ACD. So let's look back up at the diagram here and outline ACD. And we look at ACD and we look at BCE, we see that they are vertical angles. So we can sit there and say that that is true because of the vertical angles theorem, and you guys are done with chapter 2. Great job, everybody. I know that learning from a YouTube video is not necessarily the best thing. I do appreciate greatly your guys' patience with this, and your willingness to move forward with us as we, get used to Mr. Boosters not being here. So, if you have any questions, again, room 202B. Check out the videos on my YouTube channel if you ever get stuck on anything, or let me know. We're all here to help. So I hope you guys all have a fantastic weekend, and I look forward to you when we're dealing with Chapter 3.